So I'm going to be talking about going from zero to machine learning, and this is meant for everyone. And actually, some of the previous talks are going to tie in very well, so that'll be pleasant. So a very brief bio. I hate doing bios, so I'll keep it super short. My name is Paul Petersen. I'm the CIO, the eyes for infrastructure. So I made all of the infrastructure for what you're about to see, which also means if it goes horribly wrong, it's probably my fault. I have a lot of technology that's all trying to work together, and it's always a bit of a toss-up whether it's going to work. So there you go. Okay, so machine learning for everyone. Key component of machine learning for everyone is to make it easy to use. That's really the most important thing. If it isn't easy to use, the barrier is too high. Fewer people use it. Fewer people is clearly not everyone. So what I'm going to do is try to show you how you can go from zero, that is nothing, to doing machine learning in just a few clicks. And at this point, I really hope that you're very suspicious, right? That sounds doubtful, it seems impossible. And maybe even you're thinking like a few clicks of Dorothy's slippers. Okay? And yeah, so I'm going to jump right into it. I'm going to do it. So to talk about machine learning, we need some data. And I'm using data from a site called Redfin. You guys know Redfin at all? Okay, so I do this demo around the world. It turns out they don't really have much of a world footprint, and so there's always like dead silence. So it's really pleasant to be able to say Redfin and have everybody go, yeah, I know that. So the cool thing about using their site is that you can set a filter. These are homes in Corvallis, by the way. And once you've done that, there's a little download button over here, and if you hit that, you get a CSV. It comes down into your browser. And so we've already got some data we can play with. Yeah, that's super nice. And so let me upload this data and play with it. So this is our Big ML UI, and I'm going to show you what we can do with this Redfin data. So in particular, I have the prices of homes that were sold in Corvallis over a 6-month or a 1-year period or something. And let me show you what kind of data we have in here. Okay. So at this step, all I'm doing is just bringing data in. We take a peek at it for you. We assign all these field types automatically, so you can see, hopefully you can see, I can make it a little bigger. There we go. So we can see we have the address for each home, right? So here's 1522 Northwest Jonquil, or Jonquil, I'm not sure. And there's a zip code, and you can see that it's discovered that the address should be a text field. And the whole point of this step is just to make sure that these field types are correct. And in this case, actually, one of them is incorrect, which is the zip code is numeric. We'd like it to be categorical, so I'll fix that. And I think the location, we can also make text. Those are the things I'm going to fix. And that's pretty much all you're doing at this source step. Now you'll notice that I'm not doing any pre-processing. Okay, it's mixed text fields, categorical, numeric. If you've been playing around with machine learning, you're probably familiar with this idea that you have to do some pre-processing normally to work with those kinds of things. We're not going to do that. It's going to happen for us transparently. And so in particular, we can look at the address and get a sense of what kind of words are in the address field. Okay, so Northwest is very dominant. I think maybe there's just more homes in Northwest Corvallis, I'm not sure. But Kings and Arthur, we can see how many homes visually are in each of these neighborhoods, essentially. And this, by the way, is what we call a data set. I just kind of clicked through it really fast. I forgot to mention, this is a much longer presentation I'm going to compress. So I'm going to accelerate as I go, and I'll apologize ahead of time. But yes, so this is a data set. This is just like a pre-flight check for doing machine learning. Some summary statistics, we can see, okay, there's like 3 different zip codes that are in here. And there's bedrooms ranging from a house with 6 bedrooms all the way down to 0. Okay, what are we going to do with this data? That's the question. And actually, since I've asked the question, I actually forgot my notes, which remind me what I'm doing. So, because I'm old, apparently. Okay, here we go. No, I know what we're doing, I'm sorry. But what we're going to do next comes up. Okay, one thing we could do is we could build a model that tries to predict this sale price, right? That would be kind of fun to do, so let's do that. Okay, and then in particular, I'm going to be doing that a lot, so I'm going to make sure that I don't forget later. This is just making that the default objective. So if I do something called a one-click action, it's going to pick that. All right, so if we configure a model, it says the last sale price, and we're not going to do much more than that. We're just going to configure a model. Okay, at this point, it's going through all of this house price data, and it's building what we call a simple model, which is a decision tree, that will predict home prices for us. Okay, what ends up at the root of this tree is the feature, and a split value of that feature that gives the best segmentation among the house prices. Okay, in this case, actually has the square footage. And that sort of matches our intuition, right? We expect the square footage to be somehow a dominant predictor. But it's important to remember that the machine has no intuition. It just discovered this from the data. But it's always pleasing when it matches your intuition, at least. And as we go down these branches, we can see more information about how these prices are being predicted. And so, for example, here we can see a house that is, or a set of houses, for example, that are greater than 3,000 square feet. I'm looking down the right here, sorry. They're a latitude of less than 44, so this is South Corvallis. Fewer than 4 bedrooms. The address doesn't contain the word spring. They're a little bit further east. The address is also not Highland, so I guess maybe these are in the floodplain. I'm not sure. But the year built is new, right? They're greater than 1986, and you can see a predicted price of $700,000 there. I presume this is because they have a great deal of land, and we have some extra error calculation there as well. I won't belabor the model too much because I want to cover a lot of stuff, but of course we can use this now to make new predictions. If I want to know if a house that's on the market is a fair price or not, I can come in here and I can input these values, whatever I'm looking at. So I say, okay, I'm looking at a 2,000 square foot home. It's got a much smaller lot than that. It's a little bit further north. And you can see that I now have a predicted price at the top there. All right, very simple. Okay, the thing that I do want to point out, though, is that you'll notice as I move this slider around, the predicted price is changing instantly. Yes? Okay, and that is because all of the resources that we create are fully exportable. And one of the slides in John's presentation, not to pick on him, was talking about if you're using machine learning as a service, which clearly we are, then the models aren't yours. And in this case, they are. Okay, they're fully exportable. We don't constrain you to the platform. They come out. You can do stuff like run them in JavaScript or Node.js or Python or whatever you like. Okay, you don't have to use us for predictions. No problem. In fact, they're so exportable, I did kind of a fun little project where I integrated it, here we go, with a voice system. So, open BigML, this is audio.
Welcome to BigML. You are logged in as Petersen demo.
Oh, yeah.
You can load the latest resource, for example, a model, set a project filter, or make a prediction.
Load the latest model.
The latest Redfin sold clean model is loading. Would you like to start a prediction?
It can't pronounce CVO, that's forgivable. Yes.
What is the square footage?
2,000. Oh, Wi-Fi, come on.
Sorry, your Echo Dot lost its connection.
Classic. Ask BigML to make a prediction. We'll try it again. Oh. Open BigML. No? Wi-Fi is the key. Open BigML. You guys are all Instagramming too much this event. I know it's very exciting, but you're going to have to delay just for a minute to get to the excitement. We'll give it one more shot, and then I'll give up. Open BigML. Oh, that's really going to hurt the end. Ah, well. So this is just the tease for the really cool demo at the end. Hopefully the Wi-Fi will come back by then. Okay. So, as you can imagine, if you imagine, I can find this. Okay. What just happened? It almost just happened. Here we go. So we took some home data. Okay, very simple. We uploaded it into some machine learning platform. This platform generated some kind of a model for us. We put that model into a voice interface, which then lost its Wi-Fi connection, so it failed to ask us questions like, what is the size of the home?
Welcome to BigML.
Oh.
You are logged in as Petersen demo. You can load the latest resource, for example, a model, set a project filter, or make a prediction.
Load the latest model. We'll give it one more shot here. Yeah, you want to? No.
I did not recognize.
Load the latest model. Wow, that was really slow.
I did not recognize that.
Open BigML. How often do we want to try? Okay. Oh, wait. It's thinking.
Sorry, there was a problem with the BigML skill.
No, there wasn't.
You might try again in just a minute.
I surrender. Okay. That's terrible. Okay. But then it returns a prediction, which it does. It's really cool. This is the exact same thing. It's like walking through the tree. And just a little bit about the terminology. Okay, so at this end, we call this consuming the model or putting it into production. And you can do this. You could imagine doing this in some kind of a dashboard or a custom application, a wearable edge device, or some kind of batch process. All right. And this bit in the middle, we call the machine learning platform, which spits out some kind of machine learning resource, which could be things like modeling or clustering or anomaly detection or association discovery. And that bit over there we like to call the training data. And a little bit about the ownership. The training data is you. Okay, this is where you come up with some kind of a business problem, like the wine example, and you have to assemble that data, and then everything over here is the magic slippers. Voice control systems accepted. Okay, so just very briefly, a little history of the company. So our mission is to make machine learning beautifully simple, not necessarily voice interfaces. Okay, I'm going to leave it alone. Okay, so we were founded in Corvallis, Oregon in 2011, before machine learning was cool. Okay, if we went to a conference like this in 2011, there'd be no one here. It was like, machine learning as a service? Like, what's that? Okay. In particular, it was long before Microsoft, Amazon, Google, and all the rest of these players said, hey, there's something here. We could do something cool with that. In fact, they've all tried to buy us at one time or another. That's another story altogether, to be told over drinks. Okay, why Corvallis? It's the most innovative city in the United States. I'm sorry, Portland. You're really close. You're like our big brother. And we look up to you, but see? Data. Yeah. Okay. So our strategy is to hire where the best people are. So it doesn't matter where we are. So if you live in Portland and you want to work for us, that's no problem. And so actually from day one, we were an international company, half in Spain, and now we're actually a little bit in China and South America and all over the US and Europe as well. Okay, our secondary strategy and the approach side is on education. So we actually make machine learning for everyone. This is our goal, and so we focus on education. One way to do that is these free 2-day summer schools around the world where we actually talk all about machine learning and how to do it. We give out free pro-level subscriptions to all schools and universities and a free basic plan for everyone. Okay, so on the other slide where the machine learning service had $3 signs, ours would be no dollar signs. It doesn't have to be that way. It's just the big players that are trying to charge you too much. Okay, the platform itself. Smart infrastructure, that's the piece I wrote, manages the cloud. Hopefully everything's working right now. Manages the distributed machine learning backend, creates a REST API. So that part makes machine learning easy, having a REST API. If you're software developers in here, we were one of the very first. The only thing that really beat us was the Google Predict API, but I don't think that qualifies as a machine learning API. So that makes things easy. Then we have a web-based front end, which gives you some visualizations. The visualizations make it easy to interpret and understand what you're doing. And then we've created a bunch of tools, which make that easier as well. Command line tools and a voice interface and other things like that. Okay, I made that was my sales pitch. It's very short because I'm not a salesman. Okay, I want to talk about model choices though, because this also came up in an earlier talk as well. So the single decision tree was really easy to understand, right? I showed you it's split on square foot, and that was great. Gives you some kind of a deeper understanding of what's going on. But could we build something stronger, right? We already saw neural networks too. So there's actually hundreds of algorithms. If you haven't read this paper, it's a great paper. Do we really need hundreds of classifiers to solve real-world classification problems? Has anybody read this? Aye, so one, okay. I mean, I wouldn't run out and read it or anything, but it's a good read. So they take 179 classifiers, it says there, from 17 different families, and they run it across the entire UCI repository and a bunch of other data sets, and they discover that really the random decision force is always in the top 3, so you don't really need all 187 or 179 or whatever it is. And we take this to heart, so we've really focused on implementing algorithms that are the best in terms of interpretability and the ability to work with real-world data. Okay, that's where a lot of these algorithms fall down. So single decision trees, logistic regression, decision forests, random decision forest, boosted trees, and deep nets, deep neural networks. But wait, those are hard, right? Has anybody here done a neural network implementation and solved a real-world problem? Okay, solved a laboratory problem, just for fun. Okay, was it hard? Yeah, a little bit. Okay, so let's talk about why. So here's a structure, and this is actually a structure that you would use to do the iris data set. Okay, we have 4 features, right? The different kinds of ways you can describe an iris flower in one of the 3 classes, and there's some hidden layer in the middle. And now we start thinking about, well, there's some activation function we got to put over there, which is like some kind of a big logistic regression sort of thing going on there. And maybe we'll put another layer, and we'll add another one, and this one can have 3,000 nodes or something. I don't know. It just turns into a big quagmire, all right? And you'd think that was okay. Well, we'll just suffer through the quagmire and everything will be fine. But no. The success is dependent on getting the right network structure. All right, if you get it wrong, it goes horribly wrong usually. And there are just far too many parameters. There's the nodes, the layers, the activation function, the learning rate, and setting them takes significant expert knowledge. So we have 2 solutions for you. One is meta-learning. So we built about 250,000 deep neural networks and found the ideal network topology for each one, and then built a new training data set that was, if your data set looks like this, your network topology should look like that, and then we modeled that. So when you give us a data set, we go, it's probably this. That's pretty good. It's like a good initial guess. And then we also have a network search, which if you're familiar with these words, is a Bayesian parameter optimization. Okay, so it's a network search. It tries a couple of different structures, looks at how they perform, predicts what the next structure will work best. All right? And this is actually a pretty powerful technique, which I will endeavor to show you. Okay, so with the same Redfin data set, if we wanted to use a different algorithm, we could do that. Okay, so we take our Redfin sold file here, and instead of configuring a model, actually we can just do one click now. I could do a one-click ensemble. So here's our ensemble techniques. Actually, I could do this from here. I'll cheat. I can also do oh no, I wanted to show you the deep neural network. So now there's an ensemble running in the background. That's okay. So we'll configure a deep neural network, or we'll just do a one-click. That could work too. All right. One more time, with feeling. Here we go, configure. Okay, so if you don't like automatic as your glutton for punishment, you can do this too. You can say, okay, I want these layers, I want a sigmoid here, and I really need a ReLU there, and this has got to have more nodes. And you can tinker with this, that's fine too. Or you can use the automatic, and this will be the structured suggestion, or the network search. If you select network search, then you can tell it how many networks to evaluate and the maximum training time to take. All right, pretty straightforward. And I actually did kick one of these off. Deep nets. So here we have one. That's the search. It's searching. Okay. This one. Okay. And they look like this. It's a little harder to visualize these, so we give you what's called a partial dependence plot, where you can see this decision boundary in two variables. All right, it's a nice visualization for at least getting an idea. So we can put the square footage there and the lot size, and you can see these homes down here have a lower sale price, and up here they have a higher sale price. All right. I don't want to go too much. Okay. All right, that's great, but how do you know which one to use? Now I've given you random decision forest, logistic regression, deep neural networks. Let me give you a little guideline. Okay. So on this axis here, we're going to put decreasing interpretability, better representation, and longer training. So anything over here takes a super long time, models things better, but is really hard to understand. Yeah? Okay. And on this axis over here, we're going to put increasing data size and complexity. So anything that's up here is either a really big data file or is very complex. And I'm going to break this into three quadrants. One is what I call the early stage or rapid prototyping. This is where you have an idea, but you have no idea if it's even going to work. Okay, you've just got some data. You don't even know if you're going to be able to save your company $1 million yet. And if you're in this, you really should be working with logistic regression and single decision trees, because they allow you to understand the model and make sure you're not making any mistakes, like features that are overly correlated. Okay, this is a good place to start. And they're also very fast to train, so it's much easier to experiment with new features or different data. Okay, mid-stage proven application. Now you know you're going to save your company millions of dollars. All right, well, you might, if it's simple data, you might think about just a decision tree or a random decision forest. Those are good choices as well. Late stage critical performance, you know you're going to save your company $1 million absolutely for sure, and now you want to try to save 1.5 million. All right, or maybe you're predicting cancer, and so 1% mistake is not going to cover it anymore. So if you have simpler data, you might think about a boosted tree with a small learning rate, or if you have really big or complex data, you could deep neural network. Now, it's completely fair at this point to say this is still too hard. Yeah? I mean, we've boiled down 187 to just those 6, and it's still a bit kind of So let me introduce you to OptimL. Okay, so each resource has several parameters that impact quality, number of trees, missing splits, nodes, and weights. Rather than trial and error, we can use machine learning to find ideal parameters. Well, why not make the model type, whether you can use a decision tree, a boosted tree, et cetera, a parameter as well, parameterized model type. Okay, so similar to the deep network search, but we'll find the optimum machine learning algorithm parameters for your data automatically. All right, this is what we're going to do. Okay. So each time it's evaluating, it sees, okay, this is an ensemble, this ensemble did well, so maybe I'll try another ensemble. And so if you don't know what model you want to use, but you just want the absolute best, you can come down here and say, let's do a one-click OptimL, and now it's going to go through and try them all. Okay, this can take a little while to run, but we'll give it, oh, there we go, we got it. So it's cranking through. Okay, you can see it's already created 2 deep neural networks, so it's exploring those, 2 ensembles, and a model. It'll go through and evaluate them, and then it'll decide what to try next. All right. Okay, let's talk about workflows. Real-world machine learning applications are workflows. Everything I've just been doing doesn't really ever happen. Where you just take a data set and go click, boom, I'm done, yay. It doesn't happen. They really tend to look more like this. This is a real workflow for that Redfin data set where I'm saying, okay, I want to do something where I take my sold homes and I build some kind of model and all the homes are on the sale, and then I'll try to find all the deals on the market, okay, where I'm doing arbitrage. Okay, I'm predicting them what they're going to be worth, and then evaluating or predicting or building a model to predict what they should sell for, then predicting all the homes that are on the market, looking for homes that are deals, right? And then I want to be able to take a new city and put 2 data sets in and find all the deals. I like to think of myself as a real estate mogul, but I'm not. But this lets me play at night. I can say, yeah, I could buy all these houses. I don't. Okay, but these often require unsupervised learning too. Okay, we saw that earlier in that big tree. There were all those algorithms, and you may have noticed that one side said unsupervised. And I'm not sure much about unsupervised has been talked about, so we're going to do it right now. And the way I'm going to do it is by talking about a real-world application, which unfortunately may not work at the end, but let me try. So we're going to build a house recommender. Okay, so this is a typical way you might shop for a home, right? You look at some kind of drop-downs, you go, oh, okay, I want 2 bathrooms and, I don't know, no parking lots or something, probably in Portland, right? Well, we're not going to do that. That's boring. Here's my idea. I'm going to take all the homes that are on the market, and I'm going to sample from them, and I'm going to show it to you. I'm going to say, what do you think about that house? And you're going to say yes or no, and I'm going to show you that one. You're going to say yes or no. I'm going to show you a few more, and at some point I'm going to get tired of asking. And I'm going to build some kind of preference data, and I'm going to model that preference data, and I'll use that model to narrow the search. Okay, so they start with maybe 1,000 homes. I show you 5 or 10, and now I can show you that there's 100 I think you'd really like more. This is our goal. Okay. Recommender problem number 1. What if there are really unusual homes in this data? What could be an unusual home? How about a mansion with 20 bathrooms? That would be weird. How about a home with no bedrooms? That'd be kind of unusual. How about a lot size that is smaller than the home? Now I see you're laughing. I did too, and then I went to Amsterdam. Have you seen their houses? Look at these crazy things. Okay, so no, they're totally normal there, but they'd be weird here. Okay. Okay, we don't want to show these as suggestions because they're unusual, right? So how do we detect anomalies? So let's have a look at anomaly detection. This is going to run for a while. We'll come back, maybe we'll look at that. Okay, so we can take this housing data set and we can build an anomaly detector. Now this is unsupervised learning. There's really no parameters here. You can just run this. And what it's doing is now building a model that when you put a new house in can give you an anomaly score. I'll say this house is very anomalous or it's completely normal. And the way it does this is by assigning a score from 0 to 1. Okay, 0 would mean that it's completely normal. It's like every other house it's ever seen. And 1 meaning it's a mansion with 20 bedrooms. All right? And so the score here, this house I'm looking at right now, is a score of 0.62. And generally, this is a nonlinear scale. Anything over about a 0.6 is pretty anomalous. All right? And what we're looking at is a house in our training data set that was an anomaly. And so if we look over here, we see, okay, it's 5,500 square feet, okay, which is pretty big for Corvallis. It's almost $1 million, which is also very expensive for Corvallis, maybe not for Portland. And 5 bathrooms. Okay, so this is clearly an example of a mansion for Corvallis. This is a mansion, for sure, okay? And how about some of these other ones? So this one's a 0.67 almost. And if we look at this one, this is also very expensive, $840,000, almost 5,000 square feet, and it has no bedrooms. Okay, now this is actually missing data. Okay, just nobody put it in. They were selling this house. They figured it's almost $1 million. They don't have to tell you how many bedrooms there are. It's sort of like pay to play, right? If you can't afford it, then you don't even get to ask. No, but so in this case, we've actually discovered mistakes in our data with the anomaly detector, which is another cool thing. But if we wanted to get rid of them, we could. We could just highlight all these points. We can use this anomaly detector as a filter. Okay, and I can hit here, and now this new data set, those houses that were anomalies, they're gone. All right, so now we can do more exploration with a cleaner data set. Okay, so anomaly detectors are great. You can also use them for determining when you need to retrain. That's another trick. If you're interested in that, ask me after. I'll tell you how it works. Okay, so we wanted to find remove unusual homes. We created an anomaly detector, examined the top anomalies, found some unusual homes, and in the process discovered bad data. How can we fix it? Well, we've been seeing this pattern of using machine learning to do machine learning, right? Like optimizing a model, we can do with machine learning. Choosing which model to use, we can do with machine learning. We can fix missing data with machine learning as well. So here's our housing data, and we've got some missing values there. Okay, there's the bedrooms and the bathrooms. And what if we just took all of the rest of the data and built a model that could predict bedrooms? And then we just use that model to replace all the missing data with best guesses. We could do the same trick again. We could predict all the bathrooms, and then we could replace that one. And hopefully you're thinking that just seems like cheating. But this actually works really well, because one thing you could do is you could just ignore the data, but then you have a much smaller data set. And this allows you to sort of replace the missing values with something that matches the distribution and allow you to put that data back in for training. We've used this for real production situations. It's very powerful. Again, if you want to know more about that, happy to talk about it. Okay, but what happened to being easy, right? This is looking really difficult again. Yes? Okay, let's talk a little bit about WisML. Okay, this is a domain-specific language for doing workflow automation. And this is very small. My apologies. I'll cheat. bigml.com. Okay, this is a full Turing-complete programming language. And so you can say +1, 2 or something, and hopefully it'll say 3. Otherwise, everything's gone horribly wrong. All right, but in the same way that you can say, it's down at the bottom there. Okay, this is a Lisp-style syntax. Operator comes first. Does anybody like Lisp, by the way? Ah, yeah, this is my crowd. No? Oh, one no. Oh, that's all right. Nobody stormed out of the room, so that's good. But in the same way you can do 1 + 2, you can also say model plus dataset equals batch prediction. What I mean is all the machine learning resources are fundamental first-class citizens in this language. All right, now that still doesn't sound very easy. I mean, it sounds cool, right? But writing that program is going to be hard. Okay, I've got to learn a new programming language. But the nice thing about WisML being in a platform is that other people can write them and they can share them and they become atomic execution units that do these workflows. So in particular, there's a workflow that does best first feature selection. There's one that finds the nearest neighbors in a cluster. Here's removing anomalies. Actually, that one I just did. We could do that in a workflow. And if we scroll down far enough, we should be able to find autocomplete missing fields. Okay, and so I can actually just clone this out of the gallery. Okay, I can look at the source code if you're into that. But I can also just execute it. Hopefully this works. I just realized I deleted something earlier. Okay, but I can pass it this data set. I can say, no, don't use that. And it's now going to execute this workflow on my data set. So it's now doing exactly what I said. It's finding all the fields that have missing values and folding through and building a model that predicts that field and replacing all the missing values. And we can actually see it creating resources. There we are. So it's already created 4 data sets and 4 ensembles. It uses ensembles to do the prediction. And we'll eventually return a clean data set. We'll just let it run. I think it takes 45 seconds, but we won't watch it. Okay. This interface. We'll do it the hard way. Okay. We did this slide. WisML, there we go. Okay, so what just happened? We had a data set with missing values. We wanted to apply an algorithm to fix missing values, right? Rather than write it, we found it in the public gallery. There's lots of stuff out there. I wrote one that implements the Haversine formula. Does anybody know the Haversine formula? Yes, one hand. Fantastic. We need to totally connect. Okay, so this is for computing the distance between latitude and longitude coordinates. Okay, I implemented it in WisML, so you can actually take any data that has latitude and longitude coordinates and a reference point, and you can just clone the script and compute. Anyways, it's pretty cool. So now that we have this clone this script, we can use it again and again and again. So a new data set tomorrow, it's got missing values, click a button, boom, missing values gone. And you can write new ones too. Please do, it's fun. But let's move on to recommender problem number 2. How can we avoid showing essentially the same house over and over? Okay, so I take all the homes, I draw a sample, I show you that one, I show you those, and you know what? You say no to all of them. You're just like, no, 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 ridiculous computers. Okay, and because you're really interested in a modern home. Okay, and I'm just not showing you that. So here's one idea. We could cluster them, right? We could say, okay, what if we just take all the modern homes and all the homes that have, for example, lots of lands or something, and we'd sample from each of those. So I'll show you a modern home, you say yes or no, and then I show you one that has 10 acres and you say yes or no. And that's great, right? This gives me a bit more variety in my sample. It's smarter sampling. Okay, well, what if we don't know how to group them or how many groups of homes there should be? That sounds like a machine learning problem. Thanks for the chuckle. That was nice. Okay, so we'll take our clean data set. Yes, and I have to do one little transformation because the output of that script creates these fields that just marks whether or not they were completed. So bedroom's missing. So it has the fixed field, but I want to take this out so I know. Otherwise, they'll confuse things. So we'll do a little quick filter, patience. And this goes away. Zip code, lot size. Oh, that one too. Did I get them all? Yes. All right, so I'm just creating a new data set that removes those. Okay, so we're going to cluster it. So we'll configure a cluster. And we have two choices. One is k-means. This is where you know ahead of time how many groups you want. I want 10 groups of homes. In this case, we don't. So we can use something called g-means. And we have this little thing called the critical value, which just sort of tells you roughly how picky you're going to be about how unique those groups are. I can set that very low, and I'll get more groups in general. I'm going to enable this little thing over here that says model clusters, and you'll see why. Hint, because it's really cool. Okay, so now it's going to chug through our data, and it's going to try to group these homes. We're not going to know how it's making these groups. Okay, well, I mean, we know mathematically, but we don't necessarily understand the groups until we look at them. All right, it's just picking them all by itself. Yeah. Or it's waiting. Come on, 40%. Oh, 90%, just when I was about to give up. Okay, fantastic. So here's some groups of homes. What are they? Well, if we select each one, then we can kind of see the center. So this big group of homes here, this cluster 7, has 86 homes in it, and they all have a number of bathrooms that some are around 1.7. They seem to be about 1,400 square feet, and the year built is somewhere around 1968 or something, and they all sold for around $250,000. Okay, that's the sort of group of homes. If we wanted to have a little deeper understanding of what these groups are, we could pick a different one. I tend to like cluster 5 if I can find it. Where is it? Where'd you go? Cluster 5. Ooh, cluster 5. That's a good one. Okay. If we want to have a little deeper understanding of what's in this, we can select it, and because we did the model clusters, we can model it. And what this is going to do is build a model that predicts membership in cluster 5. The great thing about models is that they're rules, and so we can just start to get digestible information. So in this case, if the number of bedrooms is less than 4.5, it's false. It's not in this cluster. So this cluster seems to be all homes that have more than 4.5 bedrooms. Okay? So we get some kind of a deeper understanding of these clusters, which is nice to be able to do that. Even if that's not true, we can actually look at the sale price and it says, well, okay, also if they're really expensive, which seems pretty sensible. Okay, driving on. We don't know how many groups. We use g-means. A recommender will use these to create a better sampling. We also tried to understand these home clusters using model clusters. Okay, what if we could understand them better? What if we could assign the labels? That first home is, for example, in cluster 1, that second one is in cluster 3, cluster 5, and what if instead we could get rules like, hey, if it's greater than 3,000, it's in cluster 1. Okay, this is something called association discovery, and we're going to do that also super quick. So we'll come back to the cluster. We'll do it's called a batch centroid. This is just running the data set through and creating, I have to be able to type, very important. And we're going to get a new output data set. Okay, so each home now has the cluster membership assigned to it, and I can ask it for an association discovery. So we can do a one-click association. And now I could actually constrain this association discovery so it only looks for what's called the consequent to be the cluster label. I didn't do that, so we're going to get other rules too, but that's okay. They're still interesting to look at. I wonder if this. Okay, what do we get? All right, so we can see things like if the year built is less than 1955, then the latitude is probably less than 44.5. We can see that's about a 75% confidence on that rule, so this gives us an idea that all the homes in South Corvallis are pretty old, all right, which is true. Okay, additionally, we can see that if the sale price is greater than 400,000 or so, the square footage is probably bigger than 2,500. This is a great discovery tool for just sort of finding out what's in your data, looking at all these correlations. You can also do this visually and throw the labels on there, and you can dial this thing called leverage and see only the strong rules, and so we can start seeing, okay, this last sale price is also newer homes and bigger homes. And we can also see that cluster 1 homes tend to have only 1 bathroom, and cluster 6 homes have bedrooms between 4 and 3.8. I don't know how you can have 3.9 bedrooms, but apparently the model thinks it's possible. Actually, it's because we predicted it, but that's okay. Okay, so association discovery, very powerful technique for exploring your data. All right, so we used a batch centroid to add the cluster assignment. We use association discovery to find interesting relationships between the features, including the cluster assignment. Recommender problem number 3. There's much more interesting information than just the number of bedrooms and bathrooms. There's this, imagine this. Somebody who was selling this is real data, by the way, was selling this house, hand curated this information. They somehow felt that this was the most important thing you need to know about this home, right? I mean, think they probably spent at least 30 seconds writing that. Okay, must see. Okay, unfortunately, these remarks are not available in the download, and so adding them to our dataset requires crawling the website. Okay, and like most machine learning projects, preparing the data is 80% of the difficulty. Fortunately, I already did it for you. Wasn't that very cool? Okay, rather than, let's see. Let me show you what this looks like. So, oh, and I got to speed up a little. Here we go. We're almost there. We're almost there, by the way, was our company motto for the first year of development. Everything was 2 weeks away as well. I'll have that in 2 weeks. It wasn't 2 weeks. It was typically longer. Okay, so we have the same data we had before, but we also have the remarks field. So there they are, Timber Hill, Charmer, well-maintained, 4-bedroom, great property close to Corvallis, McDonald Forest, et cetera. It's all buried in there. All right, and I need to fix this because it doesn't think it's a text field, so let me fix that real quick. Because this won't work if it's not a text field. Okay. Okay. Whoop. Well, that's kind of what I wanted to do. Our own UI has betrayed me. All right, and if we look here, we can kind of see what people are talking about their homes. Lots of people talking about their kitchen and their living room and their windows and floors. All right. What I'm going to show you, though, is something called topic modeling. We're going to try to extract a deeper thematic meaning to the way people are talking about their homes. All right? And so in this case, I'll just take the one click. What it's doing is this is called a generative model. All right, so it's trying to imagine word probabilities that, sort of like the million monkeys on a keyboard that would generate Shakespeare. This is trying to imagine machines that if you tune the probability of the words a little bit, would somehow magically generate all the things people are saying about their homes. All right, and what you get out of it is what it discovered. And so we see things like, okay, this topic 0 uses living and level and kitchen and fireplace and dining and family. All right, and you can now try to assign some kind of a human meaning to that, if you will, like topic 7, deck, beautiful ceiling, views, kitchen, storage. I mean, there's lots of ways that it's a human. We could try to describe that topic. But the fact that it has acre in it tells me that these are probably out of town. Okay, so I could call that topic of home description. These are all keywords that people would use to describe their home as out of town. And for example, topic 2 is Northwest Florence, close, shopping, backyard, OSU, charming. That's is a keyword for really small but expensive. Right? So I would call these probably in town, or maybe close to OSU. That'd probably be better. Yeah, close to OSU. All right, and we can continue experimenting with this and exploring these topics. And you can now even put in a description. It'll tell you the percentage of each topic that is assigned. All right, but we can get a deeper understanding of that thematic content. I know that was quick, sorry. Okay, so we extended the home data set with the syndicated remarks field. That took me a while, by the way. We built a model, not right now. We built a model to predict the sale price and explored how these keywords discover the remarks impacted price. And we used topic modeling to create this deeper thematic understanding. Homes that are in town, of out of town. I didn't quite do this part, but this will allow us to cluster homes by deeper meaning than beds and bathrooms. Okay, so this is actually the close. The basic recommender idea, which is probably not going to work. Okay, is that we'll take all the homes on a market, we'll cluster them, and then we'll sample from the clusters and ask yes or no. We'll get a certain number of yeses or nos. We'll build that preference model, and boom. I don't know. We'll see. Could be the Wi-Fi. We'll be kind. Let's find out. Okay. Hey, what time is it? Oh? Death. What time is it?
It's 5:39 p.m.
Fingers crossed. Here we go. Recommend a house. Oh, you can do it. Recommend a house.
What about this house with 3 bedrooms and 1 1/2 bath?
Yes. I don't have a lot
What
of money.
about this house with 2 bedrooms and 2 1/2 baths?
Also. Yes.
What do you think of this 3 bedrooms, 2 baths house?
No. It's like 600,000.
What about this house with 3 bedrooms and 3 baths?
No. Okay, it takes 2 yeses and 2 nos, and then it tries to build a model of my
I
preferences.
have built a model of your preferences in your Big ML account. Would you like to hear a summary?
Yes.
Generally speaking, it seems you prefer houses where the square footage is less than 1811. Here are a few examples.
Okay, once it's built that model, it scores all the rest of the homes and shows a few more examples, a little small. Sorry, should have made that bigger for you. So, whew, there it was. Okay, and lest you think I was cheating, it really is. It really is in there. There it is. The model is actually there. Okay, the score in model. Okay, I'm done. Game off.